My name is Jose Huertas. I'm full-time professor at Tecnológico Monterrey. I work for the Mechanical Engineering Department and for the Energy and Climate Change Research Group. It's a pleasure for us to share with you guys our most recent results.
Hello everyone, I am Sebastián Martínez and I am also a member of the Energy and Climate Change Research Group at Tecnológico de Monterrey in Mexico. We have been modeling the dispersion of pollutants near roads, and now we are modeling alternatives to reduce the exposure to these pollutants.
Hi, my name is Javier Aguirre. I'm also a member of the Energy and Climate Change Research Group at Tecnológico de Monterrey. And up next, we're going to present you our latest work in which we are searching for the best barrier design in order to protect the people that live near roads from air pollutants. The main motivation for this project is the fact that we know vehicles are the main source of air pollutants in urban centers, pollutants such as fine and ultrafine particles, black carbon, CO, and NOx, among others. But furthermore, we have that people living near roads are particularly vulnerable to these kinds of pollutants since they are exposed to the highest concentration of them because they are closest to where they are emitted, of course. In light of this, we have found that several studies have considered the use of barriers in the sides of the roads as a countermeasure to this dispersion of pollutants. Based on the above, the objective of this project then becomes to identify and evaluate different alternatives to reduce pollutant concentration associated to vehicle use near roads through the use of solid barriers. We're looking to minimize the economic cost for the barrier use, as well as to minimize the pollutant concentration near the road. In particular, we're looking to evaluate the effect of varying the barrier geometry in terms of shape and size, and also the barrier position in terms of distance downwind from the road, in order to best decrease the pollutant concentration near the road. In order to tackle this problem, we decided to define our study domain with these dimensions, and as a simple road surrounded with flat terrain. We also included the possibility of having a barrier in the downwind side of the road. In terms of the general scheme of the project, we begin by defining a baseline case for the study without barriers. We then define several barrier proposals with a set of geometries and positions. We proceed then to simulate these cases in our CFD model in order to obtain their performance in terms of pollutant concentration downwind. Based on the improvement of this performance, we accept or reject the barrier proposals. For the successful candidates, we proceed to estimate their implementation costs and compare them with each other in order to obtain a cost-saving and pollutant mitigating barrier. The way we modeled pollutant dispersion was using CFD, or computational fluid dynamics. This method consists of solving the governing equations of fluid flow for a given domain of interest. These equations don't have an analytical solution in their general form, but can be numerically approximated when we take our domain and discretize it in the form of a mesh. We then use a specialized software, in our case we use ANSYS Fluent, to compute our specific solution and obtain variables of interest, such as the wind speed distribution of our domain. It's also important to mention that several assumptions were made for our model, which simplifies our problem, and that a turbulence model was also additioned in order to deal with the inherent closure problem of these equations. The particular turbulence model we used is the K-epsilon model, which is a two-equation model that is additional to the governing equations. This model helps define the atmospheric stability of our problem, which according to our previous studies can increase pollutant concentration in roads significantly. For this project, we considered neutral atmospheric conditions, which according to different experimental studies are represented with these initial values for the turbulent kinetic energy and the turbulent energy dissipation in our simulation. In order to calibrate our model, we first proceeded to generalize our variables of interest using dimensional analysis. In particular, we defined a dimensionless concentration of pollutant, a dimensionless distance downwind from the road, and a dimensional barrier height. We then proceeded to replicate the conditions of the Idaho Falls experiment in our CFD model without barrier. With this, we found a high correlation between the downwind concentrations of SF6 measured without barrier and the one predicted by our model, successfully obtaining the baseline for our project. What we are seeing now is the wind speed distribution of a transversal plane in our solution domain, here without any barrier and here with a straight barrier. As you can see, the velocity profile across the downwind direction is maintained in the baseline, but is heavily modified in the presence of a barrier. In particular, we identified two very distinct behaviors in the region before the barrier and the region after the barrier. These behaviors are also reflected in the pollutant concentration downwind for different barrier heights, where we can see that pollutant accumulates differently depending on barrier height, resulting in higher concentrations in this region, but then decreases in a similar fashion to the non-barrier case, except with a reduction factor. It's important to note that the population we are trying to protect exists in this region, where we want to reduce pollutant concentration. Comparing the results of the pollutant concentration downwind for the different barrier heights versus the baseline, we found a high correlation between them, with a certain reduction factor that changed depending on the barrier height. With this, we found that the proportion of pollutant with respect to the baseline decreased as we increased barrier height. As preliminary conclusions, we have that our new road CFD model shows a high correlation with experimental data, and that so far, the use of a 6-meter straight barrier at the side of the road best reduces pollutant concentration downwind the barrier, with up to a 92% reduction. Finally, we want to communicate that this is still an ongoing research, as we are still working to evaluate our model's sensitivity to different barrier geometries and distances from the road, as well as to perform the corresponding cost evaluation for the different model alternatives. Without further ado, here we leave our contact for any inquiries or collaboration intentions, and we thank you for watching.